Okay, the next chapter in the Klein textbook is all about alpha carbon chemistry. And before we begin, I want to quickly define what an alpha carbon is. Usually it's in reference to a carbonyl compound, and the alpha carbon is the carbon that is immediately attached to that CO double bond. So this is going to be our alpha carbon. If you go one carbon further away, we've got beta, got gamma, and then we've got delta, but it's this alpha carbon that we tend to be most interested in. And the reason is because it's unusually acidic and reactive. So if we think about the pKa of most hydrocarbons, meaning most CH bonds, it's typically going to be in about the 40 to 50-ish range, meaning protons coming off of carbons are typically not considered acidic at all. However, the pKa of an alpha proton is going to be much lower. Typically, it's going to be around 20, but sometimes it's even all the way down to about 9 or 10. All right, and the reason for that is because if we pluck off one of those alpha protons, we run into a conjugate base that is resonance stabilized. All right, so let's take a look at this acid-base chemistry, and I'm going to show you a reaction with a strong base. Right now we're going to be generic, but then we'll later on in this lecture look at examples of strong bases. So let's say we have a simple ketone like acetone. In this case, we've got alpha carbons here and here. Doesn't really matter which one we pick because it's symmetric. And each of these alpha carbons will have protons coming off of them. All right, so if we have a strong base, that base is going to go after the most acidic proton, which in this case would be one of these alpha protons, and it's going to drop electrons down onto that carbon. All right, and when we do this, we're going to be left with a negative charge on that carbon, and that negative charge can delocalize all the way up to that oxygen. Again, this explains why those protons are so much more acidic than typical CH protons that we see in hydrocarbons. In this case, what we've formed is something that we like to call an enolate. It's important to remember that the ate suffix indicates that there's a negative charge, and it's kind of half alkene, half alcohol. That's why we get the enol prefix. But the ate suffix is important to remember that this means that there is a negative charge. All right. Interestingly, though, we can do a similar reaction with catalytic acids and bases. So let's take a look at that really quick. So we'll do a reaction with catalytic acid, but rather than getting an enolate, we're going to get something a little bit different but similar. So let's say we have our generic ketone. In this case, again, I'm going to use acetone. And I've got my catalytic acid. What can happen is this carbonyl, meaning the oxygen, can grab this proton from our catalytic acid and kick off our conjugate base. And this will occur under equilibrium conditions. Really depends on how strong that acid is. And we'll be left with an intermediate where the oxygen's protonated and we would have our conjugate base. However, we still have these alpha protons kind of dangling off the end here. And in this next step, under equilibrium, this can grab one of these alpha protons, your conjugate base. It can cascade electrons down and all the way up to that oxygen. And so again, just like before, we're going to be left with something that has a carbon-carbon double bond, and we're going to regenerate our acid. Like I said, this is catalytic because you put your acid in and it comes right back out. The position of the equilibrium depends a lot on the identity of the ketone and the acid that you're using. Typically, you don't get a lot of your enol out. Like we saw previously in second term organic chemistry, it really prefers to stay in the keto form. However, there is going to be a small amount of this in solution. And this is just simply called an enol. So it's half alkene, half alcohol. We don't use that ate suffix like we did up here because there's no negative charge. This is actually a neutral intermediate. We get something similar with catalytic base. And I wanted to show this reaction. So in this reaction, we're going to assume that the base isn't super strong. So we're not going to use one of our powerhouse bases. Instead, we are going to use just some sort of generic base. So typically that generic base is going to be something like hydroxide. So hydroxide's not as strong as some of our really strong bases, but same idea. It can grab this proton, and we can form a small amount of our enolate, where there's a negative charge there. We're not going to get very much of it because, like I said, the pKa of our protons here is about 20. The pKa of this conjugate acid, meaning water, is about 15. So if we think about it, or 15.7, really we've got an imbalance here. Our base really isn't strong enough because what we're generating is actually going to be the stronger acid, and it's going to push it back to the starting material side. But either way, we're going to generate a small amount of this. Right? And like I said, it's important to remember that this is all resonance stabilized. So we can kick electrons back up to that oxygen. And I'm actually going to slide this all over so we have a bit more room to work with. And we're going to end up forming a small amount of this enolate where the negative charge is delocalized across the carbon and the oxygen. All right, I'm going to redraw this water really quick because, like I said, water can act as both an acid and a base, and in this case, the oxygen could just steal this proton right back. And under equilibrium conditions, you could form some of this enol, plus you regenerate your base. So just like I said in the previous example, over here, we've got a catalytic base because it's being spit out at the end too. The amount of enol formed at equilibrium could be pretty small. Like I said, it depends on the identity of the ketone. But we will get some small portion of enol created, even though it prefers to be in that ketone form most of the time. There will still be a trace amount of enol. All right, so let's take a look at some weird examples with this. And I'll show you why the identity of the ketone matters so much. All right, so let's just take a generic example. So over here, I've got cyclohexanone, and I've got hydroxide, and this is just going to be catalytic. It's not going to be a full stoichiometric equivalent. And you can imagine that if this were to react, I'm just going to put a box here, and then we'll fill this in, and we put our products on this side, that we could form some of our enol, just like we saw in the mechanism above. So this would be our enol. And because it's catalytic, we're going to regenerate that hydroxide out. All right, so the question is, which side of the equilibrium is going to be favored? Well, like I said, typically enols aren't generated in a very high concentration. So for the vast majority of cases, that starting material side is going to be favored. And in fact, you can measure this. And we can see that about 99.99% of our equilibrium is going to be our keto form, meaning our ketone. And we're going to have only a tiny, tiny, tiny percent of our enol. All right. So then the question is, well, this doesn't seem very useful at all if we're only making a tiny fraction of a percent. But there are other situations where you get a lot more. So let's take a look at this next situation. And in this case, we've got a diketone, right? And if we think about it specifically, we've got 1, 2, 3, 4, 5 carbons here. So this would be a 2,4 diketone, meaning the ketones are coming off of the 2 and 4 position. And if we think about the most acidic position here, The most acidic position is going to be smack in the middle, because if we think about ripping off one of these protons, we could delocalize to either this oxygen on the right or this oxygen on the left, giving it even more resonance stabilization as a conjugate base. All right. So this time, if we react this with catalytic hydroxide, again, we could form an enol. And in this case, our enol is going to look a little bit different. And what you might notice here is we've extended the conjugation, right? So I did want to highlight this part and say that we've got extended conjugation here, right? So we've got alternating double single bonds. So let's make a note of that. So that tends to make molecules more stable. Furthermore, one cool feature of this is you can get what's called an intramolecular H bond. So in this specific example, because of the ketone we started with, we're actually going to get a lot more of this enol than the keto form. In fact, if you measure this, you're going to get about 70 to 90% of this enol form rather than the keto form. A lot of that depends on the solvents that you use for this reaction. All right, I'll show you one last really extreme example. And in this example, again, we're going to have a keto form on the left, meaning our ketone. We're going to have our hydroxide. And as you can imagine, if we were to form our enol, we would need to form a new double bond right there. We can't form a double bond on the other side. All right, so I'm going to go ahead and put those double bonds in there. We're going to make our alcohol up top, and we're going to make this into hydroxide as our catalytic base. All right, so if we look at this, one would say, well, now we've got even more conjugation. In fact, we've got so much conjugation, we could consider this aromatic. And the way we can tell if it's aromatic is by first ensuring that it's cyclic, planar, that it has aligned p orbitals in the entire ring, and that we've got 4n plus 2 pi electrons. And in this case, this reaction is so favorable that it really just goes 100%. In fact, I don't even know if you could isolate this because it would really, really, really want to react in order to become aromatic. All right, so let's take a look at the reactivity of these enols and enolates once we form them, because they can do really interesting chemistry. So let's start off on that. All right, so let's first start with our enol. That's the one that's half alkene, half alcohol. And it's important to remember that it does not have that negative charge. And it would look something like this, just generically. And if we think about resonance contributors, we can move those lone pairs down. And we could show this as a resonance structure. The Zwitter ionic form. It's going to be a minor contributor compared to the neutral form, but it shows us where the reactivity will take place. In particular, this site with the negative charge is going to be a good nucleophile, because that's the position where we've got high electron density. So this can do a lot of nucleophilic chemistry like we've seen in previous chapters. All right, let's take a look at enolates. And enolates are going to be a little bit different, a little less intuitive, but they too have two resonance contributors where you can use this negative charge, knock it down to that carbon, and show it like this. And just like we've seen before in the example above, this carbon can act as a good nucleophile. Students will oftentimes bug me though, and they'll say, well, this form over here is the major contributor. What about the oxygen? can this oxygen be a good nucleophile? And the answer is yes, but it's not as common. And in fact, they don't even cover it in our textbook. So we're just going to make a note here, and we'll say that the carbon is a good nucleophile, but this oxygen is also a good nucleophile, but not really used as often. So as far as we're concerned in this chapter, we're going to be really focused on that alpha carbon, meaning the carbon right here with that negative charge or a high electron density. That's the carbon that's going to be super reactive, and that's the one we really want to focus on. Okay, so let's just stop there for a while, and then when we come back, we'll start reviewing a little bit of our acid-base chemistry so we can look at appropriate bases for each of these reactions.